Assalamualaikum everyone. Welcome back to Easy Taleem. Today we begin the final chapter of the entire AS Pure Math syllabus. Just think about that for a moment. Over the last few weeks, we have completed functions. Let me write those down. Coordinate geometry, circles, circular measure, and we did the entire trigonometry. We did series, and last week we also finished differentiation, right? Now, and today we begin integration. Once this chapter is complete, you have officially covered every P1 topic in Cambridge AS Math 9709/12 syllabus before moving into intensive past paper preparation. The syllabus places integration immediately after differentiation, right? In P1, emphasizing it as a natural continuation of calculus. Now, let me ask you something. In the previous lectures, I asked questions like if you could differentiate x to the power of 4, right? We also differentiated 5x to the power of 7. We also differentiated the surd of x. We also differentiated the reciprocal functions, right? We did all of those, right? By now, you've become quite comfortable with differentiation, but today I'm going to ask the opposite question. Suppose I tell you that 8x to the power of 7 is not the function, rather it's the derivative of a function. So can you tell me what the initial y was, right? Now, this is where integration begins. So in differentiation, the y is known, right? Original function. Now, integration isn't a new word. It is simply the journey back. So integration is where you derive the original function from the derivative function. Let's keep it like that. Now, imagine I erase your homework. I don't erase the derivative. I erase the function. The only thing left is dy by dx is equal to 6x, right? This is the only thing left. You're not aware of what this function was. Can you reconstruct the original function? That is exactly what mathematicians Isaac Newton and Wilhelm Leibniz spent years thinking about. The Cambridge text introduces integration as a reverse process of differentiation and highlights its historical development by Newton and Leibniz. Newton and Leibniz. Integration answers that question. Now, let's start with something easy. So, if you're given y equals to x cube, if you had to differentiate it, the answer is going to be simply the power becomes the coefficient and the power gets reduced by 1. So, this is nothing but 3x squared. Now, if I ask to reverse it, if I ask you to reverse dy by dx, which is 3x squared, if I want you to come back to the original function, which is unknown right now, so can you come back? Of course you can. You will say that, okay, we reduce the power, so let's increase the power by 1, and we multiplied this 3, the original power. So now let's divide the new power, right? So we just reverse the entire process and we will come to x cube. However, is this correct? No, this is not correct. But let's give you a few more examples. If I give you a derivative function, by the way, remember that x cube is not the integral of 3x squared, while 3x squared was definitely the differential of x cube, and we will come to that. Now, if I ask you to integrate 20x cube, and by the way, the integral operator is this, right? So this gives us y, and here I am going to add a 1 and divide by the new power, that is 3 plus 1, that is 4. So this is going to become 5x4. Again, 5x4 is an incomplete answer. This is not the correct answer. Now, a lot of students think that you eventually are going to land at 5x power 4, which is excellent. But how did you know? Nobody memorized that. Your brain simply reversed differentiation, right? That is exactly what integration is. Now, the most important discovery is, remember what I told you, that this is not the correct answer and this is not the correct answer. I'll tell you why. So we did that if y is a function, if y is x cube, then dy by dx is, okay, let's create a table. So y and dy by dx. So if x cube is a function, then 3x square is the derivative. If x cube plus 8 is a function, then 3x square is the derivative. If x cube minus 1 million is a function, then 3x square is a derivative. If x cube plus whatever, some quantity plus half is a function, then 3x square is the derivative, right? So can you see that how many different functions produce the derivative? So there are infinitely many. So it's a family of functions we are chasing. Infinitely many functions produces the same derivative, right? 3x square is the so basically x cube is this graph, right? And x cube plus some coefficient is the vertical translations, right? Now can you see that the derivative functions of all these identical parallel functions are all the same, but the constant just, it tells you exactly which graph we are talking about, right? Therefore whenever we are integrating x cube with respect to x, or 3x squared with respect to x, we will write 3x cube upon 3, which is nothing but x cube. And we will also write a constant of integration because we do not know the exact vertical placement of this x cube. So if it passes through the origin, then of course x cube is like this, but the same derivative function will also be of this graph and of this graph and of this graph and of this graph. So unless we know one position at which this graph is passing from, we cannot really tell the exact function, right? So this is why we always put, whenever we are integrating a function, let's say this is any function and this is the integral, capital F is the integral of that function, we will definitely put a constant of integration. This is called the constant of integration. You forget to miss that, you lose a lot, you forget about getting the 100% marks, right? So c could be equal to pi, it could be equal to negative 17, it could be equal to ln 5 or whatever, right? Now the derivative of every constant is 0. So if you reached to a derivative of 3x square, it could have been reached from the original function of x cube plus 8 or x cube plus 9 or x cube minus 20 or x cube plus 100 upon pi or whatever, because the derivative of this constant is always 0, right? So we lost it here, and now we have to regain whatever this was. Okay, this is why every indefinite integral means when there is no limits, and we will come to that in at the end of this lecture. So I was saying that every indefinite integral includes an arbitrary constant of integration. Let's put this word to it as well, that this is an arbitrary constant of integration. So your textbook derives this by showing that infinitely many functions differ only by a constant yet have the same derivative. Like I told you that this quadratic function and this quadratic function and another translated quadratic function and this quadratic function are all going to have the same derivative function, right? Now, so what conclusion did we come to? That if this is the function, the integral is going to be x cube, but you have to put a constant, arbitrary constant of integration. Now, so a general definition is that if you are integrating ax to the power of n, where a and n are constants, then that's going to be ax n plus 1, and you divide by the new power and you put an arbitrary constant of integration. So I want you guys to note it down in your notebooks. Now, if you forget plus c, Cambridge can deduct a mark, not because they are being harsh, but because mathematically your answer is incomplete. You're not really talking about whether your function is like this or like this or like this, and you are not even leaving the possibility of you considering a lot of them, because x cube is just one possibility like this, right? However, you have to say that we don't have sufficient information to deduce which one of it is like this, so we leave a constant of integration, right? So in Desmos, if you write x cube plus c, it's going to give you a slider for c, and then you can range it on the right and left, and your graph is going to move up and down with the movement of the slider. Okay, you can go and explore it. Now, what does this integral symbol mean, right? What is this strange symbol? A lot of you will say that this is the integration sign. Okay, correct. But where did it come from? It is actually a stretched version of S, which is for sum. Okay, because later integration becomes adding infinitely many tiny pieces together. So if this is a function and you're trying to find a definite integral, so we are talking about a summation of these tiny strips from x is equal to a to x is equal to b, right? We will come to that in our next lecture on Saturday. Now, today, don't worry about that. For us, the simply means that find the original function, right? If you're given a derivative function, we have to find the original function. Now, if you have to integrate x to the power of 4 with respect to x, it's simply the constant, the coefficient is just 1, so forget about it. So this is going to be 4 plus 1 upon 4 plus 1 plus c. That's it. As simple as that, right? So nothing new. So now, if you see, if you had to differentiate x to the power of 5, it's nothing but 5x4, right? So the reverse process is x5 upon 5, right? x5 upon 5 plus c, right? Okay, so you should be noticing a pattern here, that students eventually realize that you increase the power by 1 like we put in our definition, and we divide by the new power. So I can write it down here in words: increase power by 1 and divide by the new power. Okay, if n was the original power, then n plus 1 is the new power. Okay, now the power rule of integration, let's start that, which by the way we did already. It is that if you're given a function, so let's formally write the definition. It's going to be plus 1 plus a constant of integration, and n must not be equal to -1, because if n is equal to -1, then we have to invoke logarithmic differentiation, which is not part of your AS syllabus, it is part of A2 syllabus, so forget about it. Now, in differentiation, we multiplied by the old power. Now we are simply undoing that process. So in differentiation, we used to multiply by the old power and get the differential as 20x cubed. Now we are undoing that. We are adding a power and sort of getting this 3 plus 1 out of this 20. So we are dividing it by the new power, right? So we will achieve 5x4. However, it's not the only possibility. It could also have been the same if this was any constant k, right? So we will also put a constant of arbitrary constant of integration c here. Okay, now I want you guys to quickly integrate these and leave the answers in your comments, in the comments section under this video. X to the power of half. I am just going to do this one. So if something like this is given, all you have to do is you increase the power by 1, nothing new, and the new power is 3 upon 2, and you know that if a number or a term is getting divided by a fraction, you multiply it by the reciprocal of that fraction. So I can multiply it by 2 upon 3, right? So the answer, and then plus c, so the answer is going to be 2x3 upon 2 over 3 plus c is the integration of this. Now, negative powers work exactly the same way, provided the original exponent is not -1. So let's do an example. If you have x to the 1 upon x square and you have to integrate it, now this is nothing. This is just x to the power of -2 dx. So this is going to be x to the power of -2 plus 1 over -2 plus 1 is -1, and then plus c. So this is going to become -1 upon x plus c, right? Only when you have a linear function here will this be out of your syllabus, and so you don't have to worry about getting a linear factor in the denominator. Okay, now notice what Cambridge has done here. It hasn't given you a new formula to memorize. It has asked you to understand differentiation so well that you can reverse it, and we did that in our last 2 lectures, and that's why students who truly understood the previous chapter usually find integration much easier. So far, we have answered one question: how do we reverse differentiation in order to obtain integration, right? But Cambridge isn't really interested in just one term expressions, right? What happens if there are constants, fractions, several terms together? What if you are integrating 4 with respect to x? You are integrating a constant. So remember, 4 has got a 1 which can be represented as x to the power of 0, right? And now you do the same. So for x, 0 plus 1 upon new power, which is 1, and plus c. So 4x is going to be the original function, okay, for a constant 4, right? Now, and it similar is the case in fractions and a lot of terms together. What if you are integrating 4x cube plus 5x half plus 7 upon 2 and dx? So that's going to be equal to 4x 3 plus 1 upon 3 plus 1 plus 5x half plus 1 upon half plus 1, which is 3 upon 2, and plus 7 upon 2 x plus 0 plus 1 upon 0 plus 1, which is nothing but 1, and then a constant of integration. So this is going to become x to the power of 4 plus 10 upon 3 x to the power of 3 upon 2 plus 7 upon 2x and a constant of integration. So this is as simple as that. Now, how do we find the actual equation of a curve instead of a whole family of curves, which is owing to this arbitrary constant of integration? Because this shows that our cubic curve could be like this, could be like this, could be like this, or here, or in any vertical translated position, right? That's exactly what now we are going to build in our next part of this very lecture. So now, if I give you 5x to the power of 3 plus 8x to the power of 7 plus 9x plus 2 upon 3x square, right? And I ask you to integrate it. So first of all, always keep in mind that you can distribute this integrals like this. So 5x cube could become another term separately getting integrated with respect to x, added to another integral for 8x7 with respect to x, plus another integral for 9x with respect to x, plus another integral for 2 upon 3x square, where x square is in the denominator with respect to x, right? With respect to can also be written like this, so do not panic when they give you these shortcuts. Now, you can bring the constant coefficient outside of the integral sign. So this is nothing but this, and similarly this becomes x7 dx plus 9 integral x dx plus 2 upon 3 integral 1 upon x square could be written as x minus 2 dx, right? Now, when you integrate it, so this becomes 5x to the power of 3 becomes x 4 upon 4, and leave a small plus c here, and let's say c1. Then here it is going to be 8x 8 upon 8, and then I am going to put another c, which is c2, plus 9x2 over 2, and I'm going to put another c, which is, let's say, another constant c3, plus 2 upon 3 x to the power of minus 2 plus 1 is minus 1 upon minus 1 is nothing but, so minus 1 upon negative 1. So I am going to put a negative here, and I'm going to put another constant of integration, which is c4. Now, we don't know this, we don't know this, we don't know this, and we don't know this, but together they are going to form some constant. So I can just rewrite a large capital C, right? So now this is going to become 5x4, 5 upon 4x4 plus x8 plus 9 upon 2x square, and then minus 2 upon 3x, and then a constant of integration, right? So that's your integral, okay? Very important. Notice something, we only write plus c once and not plus c after every term, just like we did here. I mean, there is so don't do that. You can represent all these 4 different constants of integration by just one constant. The sum and difference rule is presented explicitly in the Cambridge text. Integrate each term separately, then add a single constant of integration at the end, and you can go to your Cambridge endorsed work, which if you don't have, you can reach out to me on my WhatsApp and obtain a digital copy. Plus 923293028485. Okay. Now, we also did the negative indices. The biggest mistake in integration isn't calculus, it's refusing to rewrite fractions using indices, right? So if you have, for example, okay, let me change color. So if you have 3 upon under root of x and you have to integrate it with respect to x, now this is simply you bring this 3 out, and this is going to be 1 upon under root of x, and you can change the surd sign into a power. So this is nothing but 1 upon x to the power of half, and apply the power rule. So bring the power up. So this is minus half dx, and now you can do exactly what we do. So x, so this is going to become 3 times x to the power of minus half plus 1 is positive half, divided by positive half, and then plus c, right? So 3 divided by half is 6. So 6x half, which is 6 root x plus c, and that's it. Okay. Now, whenever you see roots, fractions, or powers, rewrite everything first. Your life becomes much easier. Now, how do you find the actual equation of a curve instead of the entire family of curves, right? This is one of the most important applications in your AS Mathematics P1. Now, let's say that the gradient function is 6x squared, and we write it as dy by dx or y prime or whatever, right? Now, if it says that the original curve passes through 1 comma 8, now you will see, so 1 comma 8 is the coordinates for x and y and not for dy by dx, right? So what do you have to do? So dy by dx is equal to 6x squared. You apply the integral operator. So this becomes, so this cancels this cancels this, so you have y is equal to 6x cube upon 3 plus c. So this becomes y equals to 2x cube plus c. Now you don't know the value of c, but you do know that this curve passes through one coordinate 1 comma 8. 1 comma 8. So 1 is x, 8 is y plus c, so c is going to be equal to 6. So now your actual function becomes, you put the value of c as 6 here. This is 2x cubed plus 6. So this is going to be your function. As simple as that. Okay. Now the point on the curve is not extra information. It exists for one reason only, to find the arbitrary constant of integration c. Okay, this is precisely the process illustrated in your Cambridge textbook as well. Integrate first to obtain the family of curves, then substitute the given point to determine the constant of integration. You cannot put this coordinate in the differential function given here, because this coordinate is not for the differential function, right? It's for the original function. Now let's do another example. Let's say that your differential operator or your derivative function is 4x cubed minus 2x, right? And the curve actually passes through 2 comma 10. So when I integrate it, I'm going to have x4 minus x squared. I'm going to do it very quickly, and then plus a constant of integration. X is 2, so 16 minus 4 plus c is equal to 10. 16 minus 4 is 12, so c is going to be equal to negative 2. So put it back in here. So this is going to become x4 minus x squared minus 2, and that's it. As simple as that. Now, why Cambridge loves these questions? Notice what just happened. This wasn't only integration. We used differentiation. Let me write all the topics that we made use of. We used differentiation. We used integration. We used coordinates. We also used the technique of substitution in the xy plane, right? And of course, eventually we used algebra in order to find the constant of integration by substitution, right? So one question, 5 topics, and that is exactly how Cambridge designs long questions to award you easy marks. Now, let's talk about the first major trap that you are going to encounter. So if you're given to integrate 6x squared plus 4 with respect to x, a lot of students will just integrate this variable and put 6x cubed upon 3, which is 2x squared, and just write this 4 as it is and not integrate it. And so they miss this x here, because the integral of 4 is 4x, right? So they miss this, and then koi ehsan karenge and they're going to put a plus c, right? So this is horrible. You had to put this x in here, okay? So don't make those mistakes. Another major trap is that if you, for x minus 1 dx, what they're going to do is x to the power minus 1 plus 1 upon new power, which is 0 plus c, and they're going to put infinity, right? So here the power rule fails, and we cannot divide by 0. So we are deliberately skipping this today because it's outside the scope of your P1 syllabus. It belongs with logarithmic integration at a later stage in P3. Now I want you to notice something. Cambridge isn't checking whether you can remember a formula. It's checking whether you know when to apply it, and more importantly, when not to. So far, we have learned the power rule, the constant multiples, right? So how do you integrate this with a constant multiple 3, right? Sum and difference rule. What if you have a few terms and then you are integrating them, right, together? How do you separate them? Negative indices. What if you have 1 upon x to the power of 3 upon 2 and you are integrating that? So first you bring this over here, change the power into a negative, and then you plus 1 and divide by the new power and put a constant of integration. And how do you find equations of curves, right? But we are still missing one of the most useful ideas in this chapter. What happens when the expression isn't simply x to the power of n, but something like 2x plus 3 to the power of 5? So let's use the concept of reverse chain rule in order to integrate this. We'll finish today's lecture with that idea, tackle several authentic Cambridge style questions, and I'll also show you the mistakes that repeatedly cost students marks in paper 1. However, if you're not following us on Instagram, you're missing on a lot of good stuff that we post there. So we go there by the handle EASY is easy and Taleem TALEEM. And if you have any queries, just reach out to me on my WhatsApp +92 Also, I hope you have subscribed to the channel, and you are also sharing these videos with your pals and your friends. You are going to your A-level colleges. Okay. Now let's come back. So what if you have to integrate something of this sort, a linear function raised to the power of something with respect to x? So let's do an example. Can I simply just increase the power here and divide by the new power? A lot of you are going to say yes, but no, not immediately. Now, if I ask you to differentiate this instead, if I ask you to differentiate 2x plus 3 to the power of 6, you're going to apply chain rule. You're going to bring the power here. You're going to put this as it is. You're going to raise the inner function to 1 less power. So 6 minus 1 is 5. And then you're going to multiply by the inner function, chain rule, right? So now we just reverse the entire process. So if you have ax plus b to the power of n and you are integrating it, how do you do that? You reverse the process. You first increase the power by 1, reverse differentiation, reverse chain rule. Then you divide by the new power, and then you divide by the differential of the inner function, which is a, and then you put a constant of integration. Okay. And again, this n must not be equal to -1, because if it is so, then that invokes logarithmic differentiation integration. This is one of the most important formulas in AS mathematics, and this is by design, and this is by the process, and nobody has just given it to you for rote learning. The Cambridge textbook also derives this rule by reversing the chain rule for powers of linear functions, and it stresses that it applies only to linear expressions of the form ax plus b. Okay. Now, why do we divide by a? You saw that we used to multiply by this differential of the inner function. So now we are dividing by the differential of the inner function. Okay. Now let's do an example. What if you have 3x plus 1 to the power of 4 and we are integrating it with respect to x? So this becomes 3x plus 1, the inner function raised to 1 increased power, divide by the new power, which is 5, and then you multiply the denominator by the differential of the inner function, that is 3. So that's going to be 1 upon 15 bracket 3x plus 1 to the power of 5. Very easy. Okay. Now let's do another example. What if you have 5 minus 2x, where a lot of a student and then raised to the power of 1 upon 3, and you integrate it with respect to x? Now it's very simple. You just keep the inner function as it is, increase the power by 1, divide by the new power, so multiply by the reciprocal of the new power, and then divide by the differential of the inner function, that is -2, right? So this is going to become -3/8 5 minus 2x to the power of 4 upon 3. That's it. And then you put a constant of integration as well. Very important. Now let's talk about Cambridge traps. So what if you're given to integrate this, right? So can you use today's formula? You cannot, because the inner function is not linear, it's quadratic, right? It could be anything but linear, and you cannot do that. It's not in the scope of your syllabus. However, Cambridge may give you a trap. They will give you x squared plus 2x to the power of, or let's say 2x cube to the power of 2 dx. Again, you cannot do this through reverse chain rule, but what you can do is you expand the bracket. So this becomes x4 plus 2x square 2x cube plus 4x power 6. So this is the expansion, a plus b whole square. And now this becomes x4 plus 4x5 plus 4x6 dx, and now you can integrate it. It's very easy. It's just going to become 1/5 of x5 plus 2/3 of x6 plus 4/7 of x7, and then a fat arbitrary constant of integration for all the terms. Okay. Now, let's do another example. Let's do, what if you have 12x square minus 4, which is the derivative function, and you're told that the curve passes through 2 comma 18, right? So find the function, find the original function. So y is what? So y is going to be equal to 12x cube upon 3 minus 4x plus c. So this is 3, 4. So this becomes 4x cube. So now you put this in here in the original function. So 18 is going to be equal to 32 minus 8 plus c. 18 minus 24. 18 is equal to 24. So minus 6 is equal to c. Put this in here. So y is going to be equal to 4x cube minus 4x minus 6. If you think that I'm going too fast, let me know in the comment section so that in the next videos I am slowing myself down. Okay. Now, this question alone combines integration, the coordinates, substitution, algebra, exactly the kind of integration questions repeatedly found in Cambridge topical exercises. But of course, the second lecture on Saturday is going to really get you exactly to the point where you can really attempt the P1 paper, right? Now, the 5 biggest integration mistakes are: you forget plus c, you forget to increase the power, you forget that, you forget to divide by the new power, you forget to do that. Also, this one only works when this is linear, okay? And this one is that n must never be equal to -1. This is beyond the scope of your syllabus, okay? It only works for linear expressions or power -1. Now, so I want you to notice something. Differentiation asked you one question: how does a function change? Integration asks the opposite: can you rebuild the original function, right? Every question we have solved today started with a derivative and ended with the original curve. That's exactly how Cambridge wants you to think. So today we have completed the first half of integration, and let's look at what we have learned. We did the reverse of differentiation, for which was integration. We understood why the constant of integration, the arbitrary constant of integration, exists in order to represent the family of curves. We did the power rule. We did the constant multiples, right? We also did the sum and difference. So what if you were integrating this? How do we separate it, right? We also did the negative indices. How do you integrate this? We also found the equations of curve when we are given some coordinate that the original function is passing through. And we also did the reverse chain rule for ax plus b to the power of n, integrating it with respect to x. That is already enough to solve a large proportion of the indefinite integration questions in P1. Now, what's next? In the next lecture, the final integration lecture, we'll complete the chapter by covering definite integration. Also, so this is the limits concept. Okay. We are also going to do area under the curve. This is the type of questions that you are actually asked. We are also an area under and between the curves as well, right? We are going to do the volumes of revolutions along x-axis and y-axis as well, both. right? Dx and y. Cambridge mixed examination questions as well. Now, those topics complete the entire integration chapter, and with them, the entire 9709/12 series for P1 in your AS mathematics before we move into full topical and yearly past paper practice. So don't worry, the hand holding is here. Now, my message to October November 26 students. So those of you preparing for the October November 26 examination or the resets, the free resets allowed by Cambridge, if God forbid your results on the 11th of August aren't what you hope for, don't lose heart. By then, this YouTube playlist, make sure that you are subscribing to them and you're saving the link of this playlist somewhere safe. This is going to contain complete lectures for every single topic tested in P1, right? You can revise every concept from scratch completely free of cost. And if you want structured guidance, daily accountability, homework checking, topical past papers, yearly paper practice, and full hand holding, you can join our subsidized October November 26 crash course that we are starting on the eve of 11th of August. Our goal won't simply be to finish the syllabus. Our goal will be to destroy the topical past papers first, right, and then destroy the yearly past papers, okay, until you walk into the Cambridge examination hall with a lot of confidence, right? So if today's lecture helped you understand why integration first, if we were able to answer this instead of simply you memorizing formulas, then give this video a like, subscribe, and share it with a friend who's preparing for Cambridge mathematics, and do leave us a comments in the comment section below. In the next and also follow us on our Instagram, where we go by the name of Easy Taleem, EASYTALEEM. Our WhatsApp is +92 329 3028 In the next lecture, we'll finish integration and with it the entire AS pure mathematics journey. Thank you for being a part of it. Until then, Allah Hafiz.